streaming.
Sharing the slides. Okay. Sharing my screen.
Wenchen, could you just refresh the slides? I just added a couple more slides.
Okay, sure.
Wenchen, could you just refresh the slide? Looks good.
Betsy, would you like to share the screen on your side?
No, it's good. You can just present. I think it's good.
Okay.
Okay, should we get started?
Sure. Yeah, I don't think everybody it has come yet. But yeah, let's get started.
Okay, cool. Yeah, so welcome everybody to the award ceremony of the CVPR 2020 Slam Challenge on pushing the limits of visual slam. Thanks everybody for putting in all the effort trying to beat the benchmark, and I think I hope you had some fun also trying to figure out how to make this work. And of course, we are very excited to hear what kind of ideas you came up with to make this work. So can we go to the next slide? So the motivation is, we want to go. There's been a lot of success in visual applications for non-critical applications, but there's a lot of potential if these things could work reliably enough for critical applications. But in those situations, often the conditions are suboptimal, and but many times you don't have a choice, and if there is a suboptimal condition, then things can go bad. And as you all can imagine, your real-world imagery is very challenging and noisy, right? It doesn't have often, there's not a lot of texture, motion blur, underexposed, uniform texture. So there's many challenges with real-world imagery. However, this is something that many methods have not really focused on. The big focus of the methods has been on, okay, can we make them more accurate, not necessarily more robust? And that was part of the motivation of the Onera data set, was to create something that has more challenging visual appearance and really tries to increase the robustness of these methods. Go to the next. Yeah, so there's a lot of potential, and so where we want to push the state of the art, and the motivation was to kind of push towards the upper right hand corner, something that's robust and accurate, not just accurate. And then Ashish, do you want to say a couple of things? I saw that you came online.
I can take over this part.
Okay.
Hey guys.
Hey Ashish, good morning.
Hey, good morning. Yeah, Venshan, please go ahead.
Okay. Yeah. So we are very excited to see this challenge has been a great success. We received great attention from all over the world, and there's more than 6,000 views for our two challenges, and we have more than 100 participants, and we received more than 300 submissions at the end of the challenge. Before we started this challenge, we ran ORB SLAM algorithms as a baseline, as shown in this slide. The ORB monocular methods reach a score of 3.57 in our monocular track. After 3 months competition, 3 teams surpassed the ORB SLAM baseline we set up here. They are Beanfield, Current GPU Needs Bugs, BDDD, RAM, Ramo, VG SLAM, StackG SLAM, and VRO SLAM. So the best score is 0.34, which is much more higher than the baseline. In the stereo track, also the ORB slam does a little better than the monocular one, reached a score of 1.64. 4 teams surpassed the ORB slam baseline. They are burnt GPU lead bugs, Ferroram, Megvii slam, and SAIT China Lab. The best team reached a score of 0.12. So I would like to congratulate all the team for their remarkable results. So next, let's welcome Dr. Ashish Kapoor from Microsoft Research to announce the winners. Okay.
Yeah. Hello, everyone. It was a great competition. So let's announce the winners. Richard, can you move the next slide? Yeah. So the champion of the monocular track is Team Meg7 Slam. Members are Haoxian Zhang, Zheng Chai, and Xiao Liu. So congratulations, and the prize money is $1,500. So congratulations to the team again, and virtual claps from us. It was great to see so much enthusiasm among all the teams towards this hard challenge. Wengshan, next slide, please. And the run-up of the monocular track is burnt GPU need bugs. I think it also gets the prize for the most creative name as well. Members is Yixiang Min from Stevens Institute of Technology, and with prize money of $1,000. Now let's go on to the stereo track. And for the stereo track, the champion team was again Meg7 Slam. Again, the members are Haoxian Zhang, Zheng Chai, and Xia Liu. Let's go to the next slide, Michelle. Is again Burn GPU need bugs, Yixiang Min, Stevens Institute of Technology. So again, congratulations to all both the teams doing well on both the stereo and the mono tracks. So with that, Wengshan, back to you.
Okay. Right. So I'd like to thank our sponsor, Microsoft, for the prize. And so this is today's schedule. So we are very appreciate that 4 teams would like to share their methods, their experience with us in this ceremony. So they are Megvii Slam, burnt GPU need bugs, and team Ferroram, and team from Comply Advantage. Okay, so next let's move on to the talk from Megvii Slam. Due to the time difference, so the team members wouldn't join us in person, but they sent me a video recording in advance. So next, let me play the video. Wait, let's see, can you hear the sound? Just wait a minute.
Is our result on mono track. We first use core map as a baseline method. Zheng Chai and Xiao Liu are my teammates. Both of them contribute greatly to this work. This page is our result on monotrack. We first use COMAP as a baseline method to achieve 1.03 score, and then we use COMAP with loop closure to get better. After that, we use superpoint and superglue to do feature extraction and feature matching alongside the COMAP, and achieve 0.46 score. Finally, we use COMAP with superpoint, superglue, and loop closure to achieve 0.34 score, which is on the first place of leaderboard. Now I will show our solutions for monotrack. You can see first, I will introduce the pipeline of COMAP, which we used as a baseline framework, and then feature extraction and feature matching via superpoint and superglue. And the third is the dynamic threshold according to the environment. Last is the loop detection and geometrical validation. Well, we use COMAP as a baseline method. As shown in picture, COMAP first takes images as input and perform feature extraction and feature matching and then geometric verification to build a correspondence. After finishing that, then perform image registration, triangulation, bound adjustment, etc. to do incremental mapping and localization. The feature used in COMAP is safety features, as shown in left picture. When extracting safety features and use nearest neighbor search to do feature matching, there exists lots of mismatches. In contrast, when using superpoint and superglue to do feature extraction and feature matching, the result is much better. It can produce more correct matches and few mismatches. Well, dynamic threshold is another key point in our solution. The top two pictures is two match pairs in same sequence, with setting key point threshold to 0.005 and match threshold to 0.2. We can see that the number of key points and matches is extremely unbalanced. While using the dynamic threshold, the result becomes much better. So we use dynamic threshold instead of fixed threshold. Finally, we use bag of word for loop detection. Once a loop is detected, then we perform geometric validation to reject false loops, and then perform global BA. Here are some results on the test case of monotrack. Okay, this page is our result on stereo track. Since COMAP doesn't support stereo images, it just treats stereo image as two individual images. So we first implement our stereo tracking algorithm based on the framework of COMAP, which we call the stereo COMAP. And we use stereo COMAP to achieve 0.24 score. Then we use stereo COMAP with superpoint and superglue to get better. Moreover, we use COMAP to mapping with both safety features and superpoint features, which achieve 0.139 score. Finally, we add loop closure to the former method and achieve 0.119 score, which is also the first place on the leaderboard. Now I will introduce our solutions for stereo track. First, we implement the stereo tracking algorithm based on the framework of COMAP. Then we use superpoint and superglue, which is the same as the solution of monotrack. Thirdly, we use both safety features and superpoint features for mapping. At last, we do loop detection and geometric validation. Now, this picture is the pipeline of our implementation of stereo tracking method based on the COMAP. When a stereo frame is coming, we first do feature extraction and stereo matching between stereo frames, and do sequence matching between nearby frames. When perform bundle adjustment, we only adjust the left camera pose of stereo frames, and we fix the extrinsics of stereo cameras. Meanwhile, we use both safety features and superpoint features for mapping. The result shows that it becomes more robust and have much map points, so that it is not easy to track lost. So here are some results on the test case of stereo track. Also, there are some drawbacks in our method. Now we talk about further improvement of my method. First, I think we can use some structure features such as line features for low texture scenes, which are common in the test case. The second is our method needs more efficiency. It takes about half an hour to track over a sequence of 1,000 images. So here are some feedbacks about the dataset. First, I think maybe some noise can be added to image, such as motion blurrings, which are common in real photos. Second, some noise can be added to camera intrinsics, since cameras are often not well calibrated. The third is some distorted image, such as the image taken from fisheye camera. I think this can be generated in dataset. The last is the proportion of dynamic objects in some sequence is relatively small. Maybe it can be increased a lot. Well, that's all of my presentation, and if you have some questions, please contact me with my email. Thanks for your listening.
Okay, I guess this is the end of the talk from Megvii.
So there's nobody online from the team? Or from, he's not online?
Yeah, I don't think so. Yeah, so anyone, if you have any questions, please contact them by email directly. So regarding the feedbacks from Megvii, so here. Yeah, first I would like to thank Megvii team for these feedbacks. I think we are working on some of them already. For example, for the camera intrinsics, what we did for general more realistic or more diverse camera intrinsics is we can resize and crop the image as a post-processing. Then basically we can add noise or generate images with different camera intrinsics. In terms of the motion blur, so I'm thinking about given the also do this as a post processing, like given the image given the clean image we already have and the optical flow ground truth, then we can basically calculate how we can blur each pixels and generate image, simulate the case of motion blur. And for the distorted image and fisheye camera, I think definitely we can do that in the future, but in terms of the current data, so because fisheye camera might need a larger field of view, so we cannot do this as a post-processing, but yeah, potentially we can do this in the future. Yeah, also we are working on processing and we're working on more environments. Some of them include more dynamic objects, like more person, and yeah. So we will publish more data with even more diverse environments in the future. Right. Okay. Anyone has any comments or questions regarding the work here, the talk by Megvii? Okay. How about let's move on to our second team. So by Zhi Xiangming.
Okay, can you hear me?
Yes.
Okay. Can you enable my screen sharing?
Yes, enable.
Okay, and thank you, Menshan, for the introduction, and thanks for giving this opportunity to present here, to present our work here. And our work is based on our work is based on our recent publication on CVPR 20, which is about our visual odometry method, VODOR. And this is a joint work with Yiding and Enrique. And within the different categories of visual odometry methods, they are classified as like direct, indirect, and different residual densities. And our method focuses in the dense indirect field, which is not very popular, but I think have a great potential. And traditional and the popular indirect methods track for sparse or semi-dense handcrafted features, such as orb feature or curvature extrema, and they recover the camera poses and geometry by minimizing the reprojection error. And differently, our method takes a batch of dense optical flow field sequence, and which can be estimated from external methods such as PWC-net or cross-to-fine flow, and infers temporally consistent camera poses as well as a dense depth map. And we are doing this by minimizing the endpoint error between the rigid flow and the observed flow. And we integrate our problem under a probabilistic model where camera poses, depth map, and regionness maps are modeled as hidden variables, and while the optical flow fields are modeled as observed variable and subject to a Fisk distributed residue. And the Fisk residue model is an empirically validated residue model that we obtained by testing the optical flow and point error distribution. And we explored an adaptive residue model, determining the residue distribution with respect to the magnitude of the observed optical flow. And we also did a throughout KS test, and that shows the Fisk residue model generalizes well to different optical flow estimators. And furthermore, our parameterization is estimated with respect to the observed flow magnitude, respectively with linear and log linear regression. And so the key here is to correctly model the shape and the variance of the residue distribution with respect to different optical flow magnitudes. And it is also, I think, worth to mention that the model parameterization may vary with different data set or optical flow method. So a lookup table may be a more general way than the regression, but the Fisk distribution generalizes well over data sets and optical flow methods. And the overall workflow of our method is with a given video sequence input. We first send them to a unknown dense optical flow estimator to get the optical flow field sequence as our input. And then the objective of our framework is to minimize the difference between the observed optical flow and the rigid flow. And the rigid flow is obtained by warping the depth map with camera poses. And so the residues are the endpoint error between the rigid flows and the observed flows. And the next, the residues are weighted by the rigidness maps, where pixels belong to occlusions, outliers, or moving objects are downweighted in the visual metric estimation. And finally, the weighted residues are used to update everything governed by the Fisk residue model. And optionally, we can have prior depths from rectified disparity map or from the depth map of previous batch or from some kind of like local map. And that's only optional. And our inference framework iteratively alternates between updating the depth map rigidness maps and the camera poses while assuming others fixed. And for updating depth maps, we adopt a sampling and propagation scheme where the image 2D field is broken into alternatively directed 1D chains, while depth values are randomly sampled and propagated through each chain. And furthermore, instead of a standard AMLE criteria for picking an optimum depth, we introduce a maximum inlier estimation, and that maximizes for the rigidness maps. And this criteria can achieve a better accuracy, and you may visit our paper for more details. And for the rigidness maps, we are still working on the broken 2D fields. So we have alternatively directed 1D hidden Markov chains, where we post a smoothness term on the 1D Markov chain. And this can be efficiently solved using a forward and backward algorithm. And for updating camera poses, we solve for relative camera poses using scene depth at previous time step and obtain their 2D correspondences using optical flows to define a dense PNP instance. And we solve this dense PNP instance by estimating the mode on an approximated posterior distribution given by the Monte Carlo sampling through minimum P3P instances. And so in another word, we just randomly sample P3P instances from a dense PNP instance with respect to the rigidness maps. And we use the mean shift to find the mode of the posterior. And optionally, we can fit a Gaussian uniform model to estimate a more accurate mode as well as a covariance matrix. And the covariance matrix reveals the uncertainty of the current camera pose estimation. And this is very useful when you are trying to do some kind of like post-graph optimization. And this approach has a few benefits. First, it's independent, it's robust to initialization and provides very nice robustness also towards outliers. And it's also massively parallelizable on modern GPU device that usually takes less than 5 milliseconds. And plus the update time for updating the depth and the rigidness maps, and the total time for each updating cycle is as following. And in our experiments, we take 6 frames for each batch, and our method usually converges in 2 to 5 iterations. And this allows a real-time application around 10 to 15 FPS. And now we show our result on the tartan air dataset. And the left top is the video input. And the left bottom is the optical flow input estimated using the mask flow net. And the right top is the estimated rigidness maps. And for the visualization purpose, we summed them up because because we have 6 frames in a batch and we have 6 such rigidness maps. And since all the rigidness maps are aligned to the depth map over time, so you can see the borders are darker because the borders of the scene went out of the view in the batch. And the right button is, of course, the estimated depth map. And our method works pretty much good under the tartan data set. And it's also worth to mention that our optical flow network we used in this computation is not trained or fine-tuned on the tartan data set. So the input is relies greatly on the generalization ability of recent optical flow method. So recent deep learning optical flow methods really has pretty much good generalization ability. And I think such advance gives a great potential for dancing direct VO or SLAM system, which worth to think about. So you can see the rigidness maps can also segment if the scene has some dynamic stuff, and the rigidness maps can also segment it and exclude them from the visual geometry estimation. And I think the underwater scene is very challenging because if you are looking up and there's only water surface that cannot be triangulated, and the only rigid object in the scene is that's few strides of grass, and yeah, that makes the stuff very challenging. And you can see the trace of the fishes on the rigidness maps, and because they are moving objects and they are segmented from the visual dimension estimation. And it's also worth to mention that our method is still at an early stage, and for now it's only a visual geometry method and not a full SLAM pipeline. And so in the monocular track, we sometimes load the scale drift, right? Because if you are moving very challenging into a very near plane and you lost the scale, so we also use the COMAP to do a scale correction, and so the pose is from Vodor, and we use the scale from COMAP. And for the stereo track, it's a pure Vodor solution. And also our method is supposed to be an open source project, but we are still waiting for the IP lawyer to give some consent on the stuff. So, okay, so thank you for listening.
Okay, great. Thank you.
Thank you.
Thank you so much for the impressive talk.
So maybe we have time for a couple of questions.
I have a question.
Sure.
Yeah, so a great talk. It's great to see that your graphical based approach works so competitively. Do you have any thoughts on deep learning versus this graphical model ways of thinking about reasoning about about the methods that you looked into? So do you have some high level ways of contrasting a possible method that would use deep learning instead of probabilistic graphical models? And why was the particular reason that you went with the graphical model based as opposed to, in fashion methods that everyone's going towards?
Yeah, that's a very nice question, because I think for whatever for VO or SLAM, the generalization ability is pretty important. And we observed that the optical flow methods usually has a very nice generalization ability, and I think it's because the task of optical flow estimation has a very good photometric queue, and which is easier for learning. However, if you are trying to generalize, if you are trying to put the post estimation and also, for example, the molecular depth prediction task into a deep learning framework. And I think those tasks are EU post and rely strongly on semantic priors, and that limits their generalization ability. And so maybe makes it very difficult to adopt to a different domain, like a different data set, or if you change the camera parameters, and it may also have problem when you're trying to adapt to a different data set.
Yeah, definitely. I think the way you incorporated priors into the models is very impressive. So great work.
Thank you. Thank you. So yes, we are only using the optical flow because we think they have nice generalization ability.
Great. Thank you.
So we have a question.
Yeah, I had another question. Like, do you have some feedback, maybe similar to the Meg?
Oh, yes. Actually, my thought is some of my thoughts is very similar to the Megvii team. And another thing I'm thinking is the dynamic range. I think in the data set, the dynamic range seems like higher than I feel, but I'm not very sure about this. So like every frame looks like an HDR image, and I don't know if it's common in the real world. And also, I find sometimes the model is truncated by the near plane when rendering, and that also need to be careful about. And yeah, it's a very nice data set. I like it. Thank you.
Here's another question from our YouTube audience. So did you try fine-tuning your model on type layer data set?
I'm sorry, can you repeat?
Did you try fine-tuning your model on the type layer data set?
No, we did not fine-tune the model, because running our SLAM needs GPU and fine-tune also need GPU, and I'm earning for GPU by participating in the competition.
Okay, thanks for a great talk. So any other questions from our audience? Yep. Okay, so if not, how about we move on to our third speaker? Yeah, let's.
Hi, that's me.
Morning.
Yeah, our next speaker is Maxime Herrera. So please take over.
Okay. Can you see my screen?
Yeah.
Yes.
Okay.
But not full screen. We only see the slide view.
Just the slide, or not?
We see the slides, but not full screen.
Not full screen. Oh, okay. Is it good now?
Yes.
Okay, perfect. Okay, so hi everyone. So I'm Maxime Ferreira. I'm a postdoc researcher at Onera in France, where I work in the image vision learning team. And so I've been participating to this really interesting SLAM challenge. So just to start, I will give you a few information about my background. So I just graduated from a PhD in vision-based SLAM and dense 3D mapping for underwater robotics. And during this PhD, I've mostly worked on monocular visual SLAM, also on visual inertial pressure SLAM, using a tight integration fusion of the different sensors, and also on monocular-based dense 3D reconstruction. So where the goal was to reconstruct, well, perform real-time 3D reconstructions of archaeological sites by equipping underwater robots with hardware like the one presented here. And so I graduated in last December from this PhD, and since January, I'm working as a postdoc researcher on visual SLAM at Onera. So at Onera, the robotics team is mostly working with AUVs and terrestrial robots. And so my work during this time has been mainly on monocular visual SLAM and stereo visual SLAM. And because in this team, we're working on real case, real life scenarios, the goal was to design visual SLAM algorithms with a focus on real-time capacity, reliability, and robustness. And so thanks to your dataset, I've been able to, well, benchmark a little bit more of the algorithms that we designed during this time. So just to start, I will just say, well, I'm not going to talk about any deep learning based SLAM method because I think it's not yet mature enough to be embedded on robotics platform. But today, the state-of-the-art method in visual SLAM is most probably OpSLAM, which is a feature-based SLAM method. It's one of the most accurate open source visual SLAM method today. And it is based on the extraction of all features in every images and also on local map tracking in each frame. And that's actually what makes mostly OpSLAM being such a great algorithm and so accurate. It's because it's extracting features in every images, and by always tracking the local map, it manages to almost have no drift. And so it's a keyframe-based method with closing features and monocular stereo and RGBD mode. Yet it's actually a quite costly algorithm to run, and if you try to run it in real time, usually you will have wide drops in terms of accuracy. On the other hand, you have so direct methods such as LSD SLAM, SVO, and DSO. So because they are direct methods, they are relying on a joint pixels tracking and pose estimation paradigm. They're proven to be more accurate than feature-based method in textureless areas, but they are actually less robust in general conditions. And also for LSD SLAM and DSO, we can see a drop in accuracy when we enforced real-time constraints. And actually, only SVO handles really well real-time constraint, but it's less accurate and robust. And so during my postdoc, what we wanted was to close the gap between real-time capacity, accuracy, and robustness. And so what we proposed is a feature-based SLAM algorithm composed of 3 threads: a front-end thread, a mapping thread, and a state estimation thread, where the visual front-end is meant to be lightweight in order to ensure real-time processing of every acquired images. And then we designed the mapping thread to be flexible and modular enough in order to maximize the accuracy without impacting the real-time performances. And last, we have the state estimation thread, which ensure the optimization of both keyframes and the 3D map through bundle adjustment, and which is also responsible for filtering out redundant states in order to keep real-time capacity. So I will now present in more detail the pipeline of the algorithm. So for the front end, So which is responsible for processing every acquired images. We first apply a Clay algorithm on the left image, and then we build a pyramid for cause to find tracking. So the tracking is actually performed in several steps. First, we predict the current camera's pose using the motion model based on the previous camera's pose. And then we use this predicted pose in order to perform a guided course to find optical flow tracking using the Lucas-Canade method. And this allows us to very quickly track features and also very accurately, thanks to the prior we get by projecting the 3D map pointing to the image thanks to the predicted pose. And so following this optical flow tracking, we apply a classical 2D 3D Rorschach filtering by computing an essential matrix. And then pose estimation is based on PNP-like pose refinement, also called sometimes motion-only bundle adjustment, when we keep fixed all the observed map points, and we want to refine the current pose based on the current measurements. And also we use a robust estimator here, a Uber cost function, in order to be robust to potential outliers that will have remained past the tracking stage. If failure is detected, for example, because the predicted motion was not good enough or anything, we actually skip the PNP-based refinement and turn back to a classical P3P Rorschach method in order to re-estimate the pose of the camera. And then in any case, we filter key points with high reprojection errors to avoid as much as we can drift. And finally, we use the estimated pose to update our motion model. So our method is also keyframe based, and so the visual front end is also responsible for triggering the creation of new keyframe. So in order to do so, we check several criteria, like classical criteria, like the number of track 3D map points, parallax, and also the estimated motion since last keyframe for the stereo mode. And so if a new keyframe is required, what we do in the front end is only a grid-based extraction of new key points. So in order to do it very fastly, we only extract features in cells in the image which are empty, where no key points are present. Also, we compute descriptors for every tracked key points and the newly extracted key points because, well, differently than direct SLAM methods, we don't want to give up on lost key points, and so we will use these descriptors later for local map tracking. And also in the stereo mode, we pre-process the right image at this step for further processing. So as you can see, this pipeline is actually almost a fully monocular pipeline, and the only difference here is that in the stereo mode, we have one more criterion for the keyframe creation, and we do some pre-processing on the right image for next step. And so if a new keyframe is required, we then trigger the mapping thread. So the mapping thread is responsible for processing keyframes in order to populate the 3D map that we're gonna use to localize. So first, it performs a stereo triangulation. So first of all, stereo matching is done by also applying a guided course to find optical flow tracking in the same way as we do it in the front end. Then we use the non-extrinsic pose of the stereo cameras to apply a 2D epipolar filtering. And finally, we triangulate the inliers to create the new 3D map points. We also perform temporal triangulation to create new 3D map points. And then following this, we're gonna apply a local map tracking strategy. It is done quite like in Opslam use it, but instead of doing it for every frame, we only do it for keyframes in a separate thread in order to ensure real-time processing. So what we do here is we get the new keyframe local map, and then we're going to project every unobserved 3D map points in this local map into the current keyframe and search for matches using the previously computed descriptors. And this is made modular. That is what I mean by this is that we can skip this step if at any time a new keyframe is received. And so this allows us to really keep the runtime okay with the camera's frame rate. And finally, after this local mapping step, local map tracking step, we update the co-visibility graph for keyframes and then send it to the estimator. And the estimator state estimation thread is actually mostly responsible for bundle adjustment. So to perform the bundle adjustment, we perform it locally. So first we get the last keyframe co-visibility graph, then select the keyframes to optimize within this graph along with the observed 3D map points. We also select the keyframes to keep fixed in order to keep a good conditioning of the bundle adjustment problem. And then we finally apply the bundle adjustment where we parameterized the keyframes on the 3D spatial Euclidean group. And the 3D map points are parameterized as with anchored inverse depths. So we just optimize one parameter for 3D map point, and the anchor is the first keyframe observing this 3D map point. So this allows us to optimize very, very quickly our local map and to keep very good results. And following this, we apply a map filtering stage where we check for the keyframes in the current co-visibility graph, and we check for the redundancy based on the ratio of co-observed 3D map points, and we remove redundant keyframes to keep low complexity for next bundle adjustment. And also because if they are too redundant, they don't bring enough information for better optimization. And so this is actually the full pipeline for both the stereo and monocular SLAM mode. The only difference is that obviously in the monocular SLAM mode, we don't have the right image, so we don't do any stereo matching step. And for the monocular SLAM, well, we manage initialization by performing optical flow tracking until we detect enough parallax. Then we compute an essential matrix with respect to the first keyframe, extract the relative motion from this essential matrix and perform triangulation. And then we check the triangulation results, and we reset the algorithm if we detect that we are in a degenerate cases. For example, essential metrics are not really, well, the computation of essential metrics are not really robust to very planar scenes. So if many key points are wrongly triangulated, we know that we should reset the algorithm. And for bundle adjustment optimization in the monocular mode, well, we fix at least 2 keyframes in bundle adjustment, whereas in stereo mode, we were fixing at least only 1 keyframe. That is because scale is unobservable, and so it allows us to constrain the scale. And also, we only use temporal measurements to constrain 3D map points in bundle adjustment in the monocular mode. And so, okay, so next is going to be a video showing you the algorithm in action. You're gonna see blue dots, red dots, and green dots on the image. Blue dots are key points that are not yet triangulated. Red dots are key points that have been triangulated, so the ones we use to localize. And we also use the green points, and the green points are the ones that we manage to retract when doing the local map tracking. And so this is a stereo version of the algorithm, and we actually are playing the sequence at 20 Hertz on this sequence, and well, as you can see, it runs fully real time, and the results are actually really good. And And yeah, the trajectory is pretty smooth, and given that we process everything in real time, we are actually very satisfied of the results that we got on the dataset. And so
这实时的吗？
okay, and so with this method, we managed to rank third on both tracks. So given maybe the simplicity and the fact that we run completely in real time on CPU, I'm actually really excited at the results that we got here. So
You're muted now.
okay, sorry, I got muted. I don't know why, but can you hear me again?
Yes.
So just to give you some feedback about the dataset and challenge. So I think the dataset is really nice in its in the diversity of the sequences that it has, indoor, outdoors sequences, and very different motions, slow, fast, some pure rotations and everything, things that we don't really have, well, always have on the classical dataset. In my point of view, maybe some sequences were extremely hard, maybe too hard, like MH004 was a sequence within a house where the camera was most of the time going in front of purely white wall with a completely textureless wall. And this made it pretty, well, I think it's almost impossible to do something on this without, well, at least with a classical SLAM pipeline without IMU information or the like. But otherwise, it's quite nice. Maybe just about the way you compute the score. Why not choosing timestamps and also submitting only keyframes posed instead of having to submit a pose for every images in the sequences? Because this will be less troublesome to add a loop closure mechanism in the SLAM. And well, last, I think it's currently maybe the best dataset for deep learning based SLAM, because I don't think any other dataset has this amount of ground truth images, like with optical flow and depth and everything. So yes, that's my comments. And so thank you, everyone. If anyone wants more information about me or my team, you have links here. And also, just to let you know, we're planning to submit a paper about this method for ICRA. So there is no paper yet, and we're also planning on releasing the code at this occasion. So that's it. Thank you.
Thank you. Great. I had a quick question for the parameter, sorry, for the features that you're using and the tracking. I might have missed it.
Yeah, no, I think I didn't mention it. We actually compute the Thomas's score for every pixel in the image, and then well, in every cells where we want to extract one key point, we compute Harris corner based on the Thomas's score, and get the pixel with the highest value here.
And then you track those features?
Yeah,
Okay.
biotical.
Okay.
Yeah, I have another question.
Yeah.
This is more regarding the differences in the domain when you're doing SLAM underwater versus in the air on the land. Can you qualitatively describe what might be some of the differences of the technique that you talked about, if there are any?
About the differences, well, actually,
the performance difference if you were to apply the same thing underwater versus,
well,
versus just the plain ground. Yeah.
so thing is, when I was doing my PhD so in underwater, we managed to develop a monocular SLAM algorithm, which was actually kind of simpler than this one. Actually, like underwater, using descriptors is really troublesome because most of the time you're only seeing the seabed, which is mostly sand, and correctly matching features based on descriptors is really troublesome underwater. Like for example, OpSLAM does not work at all, and it's really hard to use this kind of stuff. So I actually started to use optical flow for tracking in this context of underwater SLAM. But then we moved to the tight fusion of the monocular camera with pressure sensor and MEMS IMU. So how to say, the challenges were not so much more about the visual SLAM. Like I think
I see. Got it. It's more about the sense of fusion there then.
Yeah, after that. But otherwise, the pipeline for the monocular visual SLAM was pretty much the same as here. Just we didn't have a local map tracking strategy, but it was mostly like this.
Okay, great. Thank you.
So, so for the local tracking, you're using optical flow. Yeah, you're not matching using the features.
Yeah.
And so for loop closure, you do have features for those key points, right?
Yeah. Well, we're using optical flow for frame-to-frame tracking, but we're using the features, the descriptors for local map tracking, which is kind of like local loop closure.
Okay, got it. Yeah, very matured system.
Yeah, and yeah, this is actually too, because like usually when you do direct tracking, or either in direct SLAM or when you use optical flow like this, every time you lose a feature, you will never use it again, which is kind of a shame because it has a lot of information.
Yes,
So
for monocular, you're doomed, and for stereo, you can still doing visual geometry.
yeah.
Are there any considerations for scale drift in your method?
Well, not really. It's everything is pretty much managed in the bundle adjustment, like fixing enough keyframes to avoid scale drift. But thing is, well, my point of view, when you do monocular SLAM, the only way to correct scale drift is to do loop closure detection. So the local map tracking step might help a little bit here, but it's just gonna be like local corrections. And if you have like big scale drift, I think without a loop closure strategy like the one in OpSLAM, there is no way to recover from this. But here, everything, yes, is managed in like creating fast enough keyframes and fixing enough keyframes when doing bundle adjustment to avoid scale drift.
Could you say something about your motion model? How do you determine that a priori?
Yeah, well, it's actually quite simple. We just compute velocity from the previous frame, and so we do it on SE3, and then we compute like taking the log of the relative motion for the previous frame, and then propagating it to the previous pose for predicting the new pose. I don't know if it's clear enough here, but
yes. So basically, you're just using a linear motion model.
Yeah. Sorry. Okay.
Okay, that's great. Thanks for a great talk. So next will be our last speaker. Nikhil Angular-Lakshi.
Hi, good morning, everyone.
Yeah, their team comes from Comply Advantage. Please welcome him for the group.
Can you see my screen?
Yes, yes, we can see it.
Right. So, yeah, Comply Advantage is my current employer, but I've taken part in this competition in an independent capacity. Right. So, I believe the question was asked a couple of times earlier today, whether deep learning approach might work in this particular problem statement. And that's the one that I explored. Disclaimer is that the solution that I will be presenting for several reasons didn't really feature very high on the leaderboard, but still let's move forward and see whether it's of interest to the people on this call. Right. So the intuition behind using an end-to-end approach here using deep learning was that the data set size provided, the Tartan data set, was extremely large, 3 TB. Usually one would consider using transfer learning or some previously built model when the target data set is small enough that training on it provides fine-tuning without catastrophic forgetting. And I felt in this situation it made sense to train from scratch if it was possible to wield this massive data set. End-to-end approaches have also, end-to-end deep learning approaches, I should add, also have been shown to be successful with minimal feature engineering, and I have a few references in this presentation which I can share later on if anyone is interested, whether it's robotic grasping with vision, whether it's speech, and therefore it proves it's perhaps if it's effective even in sequence learning problems. Vision, of course, we know that pure deep learning approaches which are just CNN based have been successful in several applications, and one of the most popular examples of that would be ResNet, which does not do any kind of manual feature extraction on the image to make any decisions. It's all completely deep learning, and as well as predictive analytics is just an example that I found that could possibly use based on my previous work. It also removes the requirement to compute float, depth, landmark detection, or any of the standard, motion tracking or object detection steps that you have to take in this kind of a problem. And luckily, and therefore, this kind of an approach is it's possible to train it to any VO task which has sufficient training data, and it is not necessarily going to be limited by change of environment or any kind of other limitations like that. This process actually has been going on in a lot of fields, as Professor Kapoor said earlier, where we're moving to more deep learning based approach, because as long as you have the training data, it's quite a viable approach today. So formulating the problem, the way it is done in my approach, at each time step I will feed in a pair of consecutive images and try and predict the change in position and orientation between these two images. I also maintain a memory of previously seen frame pairs, and intuitively this can probably capture things like velocity and acceleration, which can be additional pieces of information that you might want to have between two particular frame pairs that you're looking at. Practical considerations, we're going to backpropagate through time only through a fixed trajectory length number of steps so that the learning is tractable. Any time step can be considered the start of the trajectory. That means that the hidden state being provided to the sequence model within the entire framework can be 0, and therefore you can virtually pick up any image in the middle of the data set at any point in the trajectory, pick that as your beginning, and start predicting from there, and it should be robust to this. The reason why I felt like this is important is because the first images of the various trajectories that I saw in the data set did not necessarily seem to be at rest. So it was quite possible that the second image immediately was moving, and therefore I realized that if it's only ever going to learn at the beginning of every trajectories, and we have only 369 or something trajectories, it won't be robust to this. So this is another consideration. Batching sequences can have different lengths, and hence I used a pseudo random length sorting inspired by an NLP technique actually, where you try and keep trajectories of similar length in a batch but still have some amount of randomness so that there's no issues while training. And this solution that I will present is heavily based on this paper, Deep VO towards end-to-end visual odometry with deep recurrent convolutional neural networks. This one, I believe, was trained on the Kitty data set in 2D for autonomous driving, and therefore it's very different, and I have not even used their pre-existing model. Instead, I have just used a similar architecture and idea to train from scratch on this problem. Coming to the network architecture, I initially started working on my personal computer, and therefore it was not possible to use the full resolution of the image, and therefore I immediately scaled it down to half, and upon visual inspection that was not too bad. So to start off with, to get the code running on my local, I was able to use it with half resolution, and that's why that's the beginning of my network. So 6 is the number of channels because you have 2 images stacked together, so it's RGB. We have 6 CNN layers, the details of which are in the diagram, and I can share like the missing layers later as well. But essentially there's some amount of striding, a kernel, and the number of channels keep increasing as you go deeper into the network. I did not get ample opportunity to actually play around with this with these numbers, and they are to quite an extent similar to the paper that I presented in the previous slide. However, in one of the last slides of this presentation, I will also go over what can be done to improve the current network and other items. Once it's gone through 6 layers of CNNs, it's unrolled and given to 2 LSTM layers. All layers have dropout in them to increase the robustness, but it's only set to 20%. It can possibly be set higher, and once both LSTM layers are done, there's a fully connected layer to take it down to output dimension of 7, which consists of the change in position and the change in orientation in terms of the quaternions. If there are any questions, feel free to unmute and just ask me, or if they're coming in from YouTube. Multiple avenues for improvement and modification are possible. The loss function has 2 components. It's very simple. There's a MSE loss, which is scaled up by a factor of 10, and then there's the orientation loss, which is scaled up by a factor of 100. The reason I did this is because the reason why it's not scaled up by the same factor is because orientation usually is a unit quaternion, and therefore it has very small changes, and to be able to penalize the network more strongly for those small mistakes, I'm scaling it up. Total loss is therefore the sum of these 2, as well as some L2 regularization was applied. The other challenge that was there with this data set was that because it was 3 TB, I could obviously not have it on my local computer, and even when I moved to my personal cloud compute account, it was still quite an expensive ordeal to consider having a more than 3 TB sized SSD locally on the compute instance online, and therefore I implemented a streaming method to train. So the data loader that I implemented in PyTorch was directly given the paths of the data in the Azure storage, and it would at any point only store batch size times the trajectory length plus 1 number of images in the memory. So that it would be able to effectively conserve, and there would be no memory buildup as you go through iterations and epochs. It keeps clearing the memory as it does not need any previous images. Trajectory length is a hyperparameter, by the way. It is for for a fixed trajectory, so say 16. Even though the total trajectory sequence might be say 300, we look at 16 images in a row, then we backpropagate those 16, then we pick up another 16, usually the sequential 16, and then we backpropagate on that. So at any point in time, you only need batch size cross trajectory length plus 1 because you always give 2 images in one situation, so in one iteration. So yeah, you download, discard required, and it's error tolerant streaming. That was the issue I faced, that Azure sometimes just times out and doesn't tell you about it. So oftentimes training got stalled because of that, so I had to implement that as well. Approximately ensure that the total trajectory lengths in the batch are similar. So this goes back to the NLP ULM fit paper that I talked about. So ordinarily this is done to ensure minimum amount of padding when you're thinking about it in terms of sentences in a batch, where you have zeros at the end or zeros at the beginning to make the batch a perfect cube. But in this situation, it is certainly possible to have padding images of like just a black image, just a white image, but instead it's not ideal. But I am simply taking the length as the shortest sequence in that particular batch. So that's why it makes sense, and it's helpful to have this kind of similar matching, so you don't lose more than say 20 images for any of the other sequences based on the numbers I saw in the data set. Results. It was trained. I joined this competition fairly late. It was trained for less than 2 weeks on a single GPU in the cloud. Less than 2 epochs were completed in that period of time. One epoch was purely random trajectories, so lots of truncation, and one epoch was approximately sorted on the basis of the method I just told you. And I had to make a submission and stop training at that point because this was my personal account, so it was like running up a bill, and like the deadline was there. So the result was not very good. 3 times the baseline that Wenshan presented in the beginning, and very far away from the winners. But if like Wenshan suggested, it might still be interesting to present the work. So here I am. Verdict is underwhelming. Possible approaches for improvement, which is the more interesting part of this presentation, I hope. Firstly, parallel processing, distributed computing in order to speed up training, either through TPU training or multiple GPUs, or using multiple systems in the cloud. That's just implementation detail. With regards to the actual network, the sense I got was that even at this point in time, it was far too deep for training to be very effective. So I, based on the training graphs that I saw, which I have on the last slide, it appeared that it was underfitting even though it was a deep network, and therefore I want to try a couple of things. Firstly, using larger filter sizes early on, so that I don't have to maintain such a large number of channels necessarily, and it can I can have a shallower network which captures the information. Use a deeper network which is possibly ResNet style, so that it can be deeper, but it does not lose any information along the way due to the deepness, because skip connections. modified training regime similar to this reference here, where they are training an autonomous ground vehicle and to go through a maze on the basis of imitation learning. And it has a similar solution where they train the CNN alone first and try and minimize the error, then they freeze the CNN and then train the LSTM. That way you can isolate the propagation error, because the way the two models learn are different, and therefore like it can like the errors of one can keep propagating to the other through training. Randomized sampling of data across environments. So no requirement to complete a single batch of trajectories before moving on. So in the current situation, it sort of trains right until the end of the mini batch, which is either 8 or 16 or 32 different environments that I'm looking at, and then it moves on. But a more robust, better way of training, especially since it's deep learning, would be to randomly sample a starting image from multiple environments and then train a trajectory length from that. Again, that's an implementation detail, and I wanted to do it, but I didn't have the time. Ablation studies similar to the fourth point, which is to isolate the effect of the LSTM layer and the purely CNN architecture. Based on my previous experience, I find that oftentimes our intuition that we might need some continual information through various different image frames in time is not always true. So like the intuition I gave earlier was that velocity and acceleration could be something we want to know when we're looking at the 2 frames, but how true is that? Is that really required? Does it really affect the performance? Is something that I would definitely like to get answered. So I would like to try purely CNN architecture and 2 images at a time and see how that does. Completely different approach to what I'm trying, but also using deep learning is an inverse RL approach inspired by this paper, which is actually using reinforcement learning for multiple object tracking. It's one of the professors on it is Silvio Savarese. I'd just like to confirm that I'm still audible, because I got a message that my internet was unstable.
Yes, we can hear you well.
Right. This inverse RL approach is different from my current approach, but essentially it uses decision making to track multiple objects on the screen. In this case, it's usually a CCTV camera tracking people, but the reverse approach I felt could be interesting. So you have it sort of combines some of the classical approaches that the other participants who were the winners presented before me, and a deep learning approach where you sort of have this kind of a baseline model that does something quite sensible, and then you are able to leverage RL to definitely outperform that baseline sensible model. So it could be interesting to take that approach. And finally, I have a bit more to debug as well in understanding why training is happening the way it's happening, and the mainly is that there are randoms in the process in trajectory from mini batch to mini batch. A mini batch is a particular trajectory length inside a particular long trajectory. So it's like from one set of 16 to the next series of 16 to the next series of 16, and perhaps someone here has encountered a similar problem. As you can see, the blue line in the left graph is the validation, and the orange line is what's happening to the train set, but at a really fine-grained level. So it's literally 16 images at a time. It is not the clearest indication of what's happening to the whole batch, which you can find on the right, where you can see that train and valid are sort of following each other, and based on how close they are, I know these are not the best graphs because I started logging somewhere in the middle of training, but based on how close they are and how poorly the score performed, I feel like there is significant amount of underfitting happening, as in the training set itself is not able to generalize the training. The loss on the training data indicates that it's still not able to generalize as well as you want, because it's not even fit on the particular on the training data as well yet. And on the left hand side you can see these abrupt jumps in the training whenever you go from, like, for particular batches it just like jumps up a significant amount. In terms of feedback about the data set, I am relatively new to the SNAM visual odometry, kind of vision space. So I thought it was a pretty challenging data set, and I don't have anything to add from other than what the other participants already have mentioned. Any questions?
Yeah, thank you.
I have a question. So in your network structure, you have this really large feature that input you to the LSTM, right? So you have more than 20,000 parameters,
Yeah.
the feature vectors. So to my knowledge, that would takes most of your network's parameters. So why do you use such a large number of feature vectors in the LSTM?
That's a good question, and the honest answer is that this is my first iteration at the model, and I wanted to tweak a lot more things, but I wanted to first get it to a position where I at least can easily understand and debug what steps need to be taken, and it is merely an oversight. That's all I can say.
Mm-hmm. Okay.
Yeah, hi Nikhil, this is Ashish. So, pretty heroic effort, I have to say. I think it's a pretty impressive work. I think still if it's in the beginning of, of the advances. So, contrasting with, the approach from Stevens Institute of Technology where they use probabilistic graphical model, and one of the advantages there is incorporation of prior knowledge of the domain of the problem domain itself. Have you do you have any thoughts on if incorporating such prior knowledge in a deep learning based architecture would help, and if yes, what are possible ways to incorporate such knowledge in it? So just a couple of high level thoughts, and would love to know your sense.
So, in my opinion, a good way to incorporate prior knowledge for deep learning is reinforcement learning. It's been used successfully, like I said in that other paper that I mentioned. But essentially, so as an example, if you think of the event extraction problem in NLP, you have certain like a baseline model that can extract an event from a given article, and you have a very little amount of sort of label data, and the goal is that you can use reinforcement learning with this baseline model in order to query unstructured unlabeled data and a simple similarity function to determine whether that is relevant to your current decision in order to make a better decision than your baseline. So going back to your question, if you have a model which has prior knowledge, so something that is more classical computer vision oriented for optical flow or some such thing, then that can be your baseline model wrapped inside a reinforcement learning kind of framework. And since this particular model has been trained on something, you can use it to query from this large amount, like 3 TB of data, on the basis of like we'd have to come up with a relevance metric for the kind of training that we're doing, like what are the most what are the things it's most unsure about. So we can come up with certain entropy metrics for whether the decision it's making right now for this particular pose estimation is it sure about it, is it not sure about it, etc. And then if it's not sure about it, we can sort of look into this large data set for other examples that can help us become more sure about it. Like that's one idea I have.
Okay. Have you like seen, so this is, I would say, indirect incorporation of prior knowledge into your deep learning pipeline. So besides robotics, I mean, NLP, is it the only domain that's using it, or have you seen anyone in the VIO or the robotics space do similar things?
Do they use
using
prior knowledge?
Yes, prior knowledge, but I would say this is indirect, like given that you're wrapping it in another oracle, as opposed to explicit encoding of prior knowledge, the way it's done in the graphical models, where you see that the rigid geometry plus the camera parameters plus everything should lead to the optical field you're using. In that case, they are really using prior knowledge directly in the inference process. So, do you think it's possible to encode such direct prior knowledge as well? Or is the indirect encoding of prior knowledge the only possibility?
It's definitely possible to encode it, but I would.
Oh, looks like we lost him.
Uh-oh. Yeah, I think his internet was getting worse and worse somehow. So maybe while maybe he rejoins, I think he is coming. So I think one thing I wanted to.
Then he's back.
Oh, okay, there you are. Okay. Are you
Sorry,
muted?
did I cut off there?
Yes.
Right. So I will begin. Yeah. So what I was saying is that it's definitely possible to incorporate prior knowledge into your deep learning solution. You can do this in many ways. Like, for example, say you feel that optical flow is an essential step in determining the updated pose or the updated orientation of your camera. Then it's quite possible to implement it to that step and then let deep learning take over for one module and then etc. So you can definitely put your deep learning system into modules to predict things that you think are relevant. So like in this data set, you have the various steps, right? You have the flow, you have the depth thing, and you have that in the ground truth real data. So if the designer thinks that this is what will help to make that prediction, that is one way to go about it. But what I've seen in the past is that the more you try and make your neural network or deep learning solution think like yourself, there's a good chance that it doesn't work as well as you kind of expect it to, or as well as it would have if you let it make all the decisions about what it finds relevant. So especially for this situation, given that there's such a large amount of data, I would first try and give an end-to-end approach everything and see what's the best that can happen with that before I try and incorporate a prior with a direct or indirect approach. I hope that answers your question.
Yeah, great. Thank you.
Hey, you've mentioned using inverse reinforcement learning to help the pose estimation. So could you say a little bit more about how you are going to incorporate inverse reinforcement learning?
So on the basis of that paper that I read, I can share the link. What they essentially do is that they have a still frame. I mean, the camera orientation is fixed, and then they have objects or people or whatever moving through it. And what they decide to do is that they treat each object as a separate MDP problem. So like one MDP, so they've incorporated RL such that the task of the agent is to keep tracking that one object that agent has found. So you can have multiple agents on the screen at once trying to track multiple objects. And the way they are doing inverse RL there is that so they're essentially trying to learn what kind of reward function they need to have such that this works well, and their policy is fixed with regards to again a prior kind of solution that is so they have like a series of K templates that they've matched with that object over a period of time. And they do not update which template they are trying to match unless they actually lose the image. So they try and prevent tracking drift, or as I think one of the I think Enrique had mentioned scale drift. So they try and prevent that. So they try and fix which template they're using, and so they will match the templates. They will compute the FB error, and they will try and get these kind of landmarks from the object to object in that situation, and get that optical flow kind of decision made. And then they are trying to, and when it's right, then they want to try and backpropagate on that reward function so that this kind of an example gets a higher score. And so they're essentially learning the reward function there. So here we have a lot of parallels. So we have a lot of ground truth with regards to the flow, and of course at the end of the day we want to predict the orientation and the position. So we can decide, like allow it to learn what kind of reward function to have, and use our industry standard computer vision classic metrics for deciding what the next pose should be. So their policy is therefore fixed with one of these approaches, that one of the winning approaches that can be the policy, and you are deciding what kind of reward function you have, so that you can sort of maximize when that policy is right and minimize the times when that policy goes wrong. So that's like the kind of indirect approach that I was thinking about.
I see. So if I understand correctly, so you are trying to make the training more efficient by incorporate some policies and select more promising training data, or make the to decrease the uncertainty, or is it right? So this is mainly for using in the training procedure.
Yes.
Okay.
But
Cool.
when you have completed training, that means you're not going to modify a reward function anymore, and then you allow the agent to act as it thinks appropriate.
Okay. Thank you.
Okay. Yeah, thanks everybody for sharing your approaches with us. When we put out the challenge, it's a big black hole, and we don't know. There's a certain username, and we don't know what's actually happening behind the scenes. So we're really glad that you guys came together on a really short notice to put forth what you implemented and presented, and so open about sharing this. Thanks so much for doing this. We're also very happy that you gave us a lot of feedback on the data set, and I think another way to think about this is, I think a lot of the things we've heard is, you could almost think about it like a procedural kind of corruption library, or some kind of post-processing step on the data set to add motion blur, different noise, and all these things. And we also of course welcome any kind of contributions that if you want to add on top, like some kind of library to make things better, or some of the streaming improvements, or some for training, or all of these things. If you want to kind of hold them in and you guys want to contribute, we're also open to that idea, since we put it out there open anyway. So that's just something I wanted to mention. So just let us know, you know how to find us. You can just go to the website. Vention's kind of the mastermind behind this whole data set, and just let us know. And maybe one thing we could do now is if there's any kind of other open discussion that you guys want to discuss before we kind of wrap up. Open up the floor. Okay. So yeah, so thanks everybody. And then I think regarding the actual prize money, I think let's see, what's the process, Wenchan? I think you'll send an email or something like this.
Yeah.
Okay. We'll send you guys an email and then we'll figure it out how to get that to you. Yeah, it's not so easy with bureaucracy, but we'll figure it out. Okay. Thank you.
Thank you, everyone.
Thank you. Bye.
Thank you.
Thank you. Bye.
Yeah, thank you, everyone.